I'm going to try to demonstrate in this video the physics phenomenon called Kirchhoff's loop rule, which is a way of keeping track of how energy and voltage divide in a circuit. It's actually pretty straightforward, and I hope if you see this applied with real lab equipment, you'll understand the rationality. So our circuit's going to be really simple. It's going to have a battery, and its symbol for the battery is this thing right here. It's going to have a 100 ohm resistor with the color code brown, black, brown. And it's going to have a 1000 ohm resistor with the color code brown, black, red. So what we're going to do is wire up our circuit as that diagram shows. We're going to get the three voltages that are interesting: the voltage across the 1000, the voltage across the 100, and the voltage across the battery. So on my breadboard here, I'm going to put the foot of the 1000 into its own row of holes, and the other foot into a second row. Make sure they're both seated real well. Then I'm going to take the foot of the 100 and put it in the same row as one of the 1000, and then into a different row. Make sure everybody's seated real nice. And then I'm going to put the battery leads, I'm going to hook them up to the resistors. So electricity should be flowing using the standard direction of current from the positive side of the battery to the 1000 to the 100 back to the battery. And let's check that we've got voltages. Across the battery, we appear to have a voltage of 1.49. The negative sign is because I have the leads reversed from what we'd expect. So I'll write that down as V is 1.49. We'll check across the 1000 ohm resistor. We can see that this stabilizes around 1.36. And we'll check across the 100 ohm resistor. We can see it stabilizes at 0.13. So it's interesting here. There's a couple things we can note from our pattern, which is we've got about a factor of 10 times the voltage in the 1000 ohm resistor than in the 100 ohm resistor, and that is because we've got 10 times the resistance. So what we're seeing is that in terms of voltages being used up, the 1000 ohm resistor appears to be using up more of the voltage than the 100 ohm. And that's a pattern that we'd expect. But there's another pattern that's a little more subtle, and that's what Kirchhoff's loop rule is meant to show us. Kirchhoff's loop rule basically says, if you're a charge where I have this X, and you take a walk around a circuit, you should get back to the voltage you started with. So let's take a little walk. If we go across the battery, we're getting a voltage of plus 1.49 volts. We're going to then continue across this resistor, and then we fall down minus 1.36 volts. So if you do a little bit of math, that means we're now at 0.13 volts. And guess what this one takes away? This one takes away minus 0.13 volts. So we get back to exactly what we started at. Now, why is this? Well, if this is a Coulomb of charge, we can essentially be talking about potential energy, this would be 1.49 joules to get to the top, and then minus 1.36 joules, minus 0.13 joules. I think the best way to look at it is if you went on a hike up a mountain. You parked your car at the base, you went up and got 1.49 joules of potential energy, and then you took a scenic route back down. You went part of the way down, then you went the full way down. But your car is still in the place where you put it, at the base. So if you go all the way around, you have to get back to the energy you started with. So Kirchhoff's loop rule is essentially a statement that energy is conserved.